Okay, hi everyone. I'm Tom Ranzani, and I'm going to be talking a little bit about the research that we're doing on enabling robots to function in complex and unstructured environments. And the motivation behind that is basically taking robots from environment that is almost designed around them in factories and trying to integrate them into the society. And that means working in close contact with humans, inside humans we just saw before, or being able to operate in very unstructured environment. Think about search and rescue applications. And a lot of current robotic technologies really struggle to do that very well. And so what we're looking at is biology as an inspiration. If you think about animals are able to very easily live in any kind of hard to reach area or any kind of challenging environments. And in studying animals, what you can see is that their body and the way their body function is as important as the high level controller. And that sort of create a paradigm shift in the way we think about design of a robot. So we cannot really forget about the body, and the body is an integral part of how the system will function. And so the sort of fundamental question that we're looking at is how can we replicate the complexity of biological systems in terms of material, dexterity, sensor integration into artificial devices? And how can we control and leverage that complexity to operate in a structured environment? And so the first project I'm going to talk about relates to underwater exploration, very, very challenging environment, and where we're really trying to develop a robot that is inspired by the motion capabilities of the octopus to be able to navigate within this environment and demonstrate reconfigurability of its body to go from swimming, manipulation, underwater crawling within a single robotic platform. And this really entails developing new actuation technologies that can go from a very small form factor to a large robot that can provide dexterity, but they can also use the environment. So they can squeeze in and use the environment around them to perform more efficiently a task. And as you increase, as you start to approach the level of complexity of natural system, you realize that you have all these different degrees of freedom, all this dexterity that you have to control. And this is something that we're working really hard on. So like, how can we embed on board computation and control capabilities of our soft robots to improve their autonomy in the way they're navigating inside the surrounding environment? And we're doing that by designing and synthesizing magnetically responsive materials and controlling them through magnetic field that we can control through electric fields to really be able, again, to embed part of the control function inside the robot itself. The other line of research sort of looks at the use of these technologies that we learn, again, from how natural systems use their body to medical and surgical applications. And I'd like to highlight these two specific projects. So the one on the top, we're really looking at how we can use soft materials to be very delicate, gentle, and atraumatic in the manipulation of organs. And we're looking specifically at large organs, which are really challenging to manipulate with current instrumentation if you approach them in a minimal invasive way. We're also looking at how we can embed distributed sensing on our devices and how we can use machine learning to interpret this sensor information to optimize the interaction within the tissue and the tool. The second project, it's something I'm very excited about because we picked one of the most challenging environments we could think about, and that's the beating heart. Think about the beating heart. So you have soft tissues, you have blood, everything is moving, you cannot see anything. So it's a really, really complicated scenario to work with. And that is why a lot of procedures, a lot of the current instrumentation really struggles to perform effectively a procedure to provide dexterity and force transmission at the site of operation. And that's why a lot of the times an open heart approach is required, which is very invasive. And so we're developing a robotic system that is able to really exploit the interaction with the tissue, brace at the entrance of the heart, and provide again dexterity and force transmission inside the beating heart. And we're looking at a lot of different procedures that this new technology can really enable. And I'm out of time, so I really wanted to squeeze in a thank to the amazing student that I have the pleasure to work with every day in my lab.